All right, welcome back to microeconomics in the new year. So, in this very first week after the holiday, we will finalize the second topic of our course, which is production and supply, by looking at the profit maximization problem from input perspective. And then we will already go into the first part of the last topic, which is the coordination of demand and supply via market. But first of all, we will look at some introductory concept of game theory. So let's go. So remember last time when I introduced the profit maximization problem to you, I already mentioned that it involved both choosing the output quantity and also choosing the input in order to maximize the profit. So last week or last year already, we already look at the first aspect where we only look at the output quantity, focusing on choosing the output quantity in order to maximize the profit. And now we turn our attention to the input use. So why? Because the output is determined by the amount of input the firm chooses to employ, right? So we could turn to this perspective and look from the input angle to see what happens. And the relationship between inputs and output, like in the first week of production and supply, I already said, right, is summarized or is expressed by the production function. Yeah. So because of that, we could write the profit function or profit definition of the firm as a function of inputs instead of output. So this is what we looked at last time from output perspective. So now we look at input perspective, where we plug the output quantity, the Q, by the production function F, a function of K and L, minus the cost, and go back to the original definition of cost, which is the sum of input costs. Here we have capital, the quantity of capital times its price, and similar for labor. And this is what we're gonna look at this week. Now, so here, before we go further, note that there is one important assumption implied in this setup. That is, we take P, the market price, and the prices of input V and W as given. So the assumption here is the firm is price taker. Any decision it makes concerning output or input quantity will not affect the market price of these inputs and output. Now, okay. Now let's have a look at the first order condition of the profit maximization problem from input perspective and see what is their implication. So I wrote down already the new setup from input perspective. So now we maximize the profit with respect to input use, K and L. And the definition of profit now can be written as the function of K and L. We plug K and L in the production function, the output quantity, and in the cost. Now, so now the first order condition will become the first one. We have two variables here, two inputs. So we have two first order conditions, right? The first one is the derivative, the first order derivative of profit pi with respect to K equals first term, price taker, so P constant, write it the same, df, the derivative of f with respect to K, right? Minus the second term, that is V equals 0. So that's the first equation of the first order condition, and we could already rewrite it as P market price times what is the derivative of f with respect to K then? It is actually the marginal productivity of K, right? We had that before, equal V, so denote 1. The second equation is the first order derivative of pi with respect to L, which is now P times df over dk, sorry, dl, yeah, L. Now, which is the marginal productivity of labor. Let's save it for later, minus W here equals 0. So that means P times marginal productivity of L equals W. And this is the second equation. So let's stop here for a moment. So the first order condition of the profit maximization now says that on the one side you have the market price of the input, and what is on the other side. So this is MPK is the marginal output of K, how much output you get from employing an extra unit of K, right? And when you times the market price of the output is actually the marginal revenue of K. And here similarly you have the marginal revenue of L. And here is the marginal cost of V and the marginal cost of W. Why? Because you want an extra unit of B, you have to pay its price, which is V, exactly V times 1, right? So the first order condition again says that in order for profit to maximize, your marginal revenue of employing an extra unit of input, any input, must exactly be the same as the marginal cost of buying that extra unit of input. Why equal? Why is not smaller or larger? Because, for example, if on the right hand side, on the left hand side it's smaller, so instead here a smaller sign. That means what you gain or what you earn from employing that unit of input capital is less than what you have to pay for it. And in this case, your profit is not maximized, right? So you better don't employ that extra unit. And if it's larger, that means you can still increase using that input and obtain extra profit. And in both of these smaller and larger case, your profit is not maximized. Only when it's reached the same marginal cost, the profit is maximized. So that's the first thing. Now the second thing I want you to see is, if we divide equation 2 to equation 1, we will get on one side P times MPK, sorry, MPL, because we divide 2 by 1, right? Over P times MPK. And this P and this P is not the same, right? The first one is the market price of output, and the second one denotes productivity, right? Equals W over V. Now, and we could already simplify P here. So what remains? MPL over MPK. You still remember what it is? It is the marginal rate of technical substitution of L for K, right? We had that in the cost minimization, equals W over V. And if you recall further, this is exactly what said by the first order condition of cost minimization. So you could check, oh, this is too early, minimization now. So you could check again on your own to see if this is the case. And the implication is the first order condition of the profit maximization problem from input perspective implies already cost minimization. Keep that in mind. We will need it later to explain something else. So now, if we solve for FOC, first order condition, like we usually did before, we will get the solution for K and L, right? So K star and L star, which is now a function of all the parameters except K and L in here. So what do you have? P, stay constant now, and V and W. Similar for L. So again, these are called input demand function, right? But what makes them different from the one that we obtained from the cost minimization problem? Can you point it out? What makes the difference now? So the difference is now K and L is no longer functions of Q. Before, instead, in this place we have Q now, and now we have P. We don't have Q anymore. No. So it doesn't depend on the quantity, but on input and output prices. Because of that, we call it unconditional. Remember, before, when we have Q in this place, we call it contingent input demand functions, because contingent on output quantity. Now we don't have output quantity, so it's unconditional. So what is the implication of unconditional then? What makes it different from before? It implies that from now can freely adjust their output quantity as prices change. Either input or output price changes now. So for that reason, it's unconditional. Alright, let's have an example with the good old Cobb-Douglas production function. However, now I decided to make it a little bit less drier by at least substitute some numbers in the production function. So let's put it in our profit maximization problems. Now from input perspective, meaning with respect to K and L, pi equals P times Q or times F, and in this case F is like this, and we have A equals to 4. Now K to the power of 0.25 and L to the power of 0.25 minus KV plus LW in brackets, nothing changed over there. Let's go further with the first order condition. The first one saying that the derivative of pi with respect to K, which is now P, stay the same, 4 stay the same, times 0.25, right? K to the power of 0.25 minus 1 is minus 0.75, right? And L to the power of 0.25 stay the same, minus V equals 0. This is the first equation. Now the second one. Derivative of pi with respect to L equals P price times 4 stay the same, 0.25 we also have here, but however, keep in mind that this is the exponent of L, not K anymore, because we're taking the derivative with respect to L. Alright? So that means K to the power of 0.25 remains the same, and L to the power of now minus 0.75, and minus W equals 0. And this is the second equation. I think that would be hard for you to realize. So let's make some boundaries. Okay. Now let's divide this time 1 over 2 to see what happens. Let's put it equivalent now. But before divide it, let's put V and W to the right hand side implicitly in your head. So on the left hand side we have P is gone, 4 is gone, simplified now, divide, so everything here is gone. Now come to the part of K. So you have K above and below divided by the power of 0.75 means times to the power of minus 0.25 now, and you already have on the numerator minus 0.75, so that at the end minus 1. So K to the power of minus 1 times L to the power of, now similar thing, but instead of minus, you plus, right? So L to the power of 1 equal V over W, or equal V times W minus 1, right? And you could already here cross multiply K to the other side also to have L along on one side, right? So equivalent to L equals V times W to the power of minus 1 times K. And this, let's call it equation 3. Yeah? Now we substitute 3 into 1. You could also substitute into 2, no? To solve for K star. And that is, we would have 1 is now equivalent to 4 times 0.25 is 1, right? P stay the same over there, even though like here we simplify, but when it's alone, it's still there. Remember, don't forget that. Now, and then K to the power of minus 0.75 times L. L is the whole term, so it needs a bracket. V times W minus 1 times K, right? To the power of 0.25. Alright, let's simplify it. Sorry, we still have something minus V, but let's put V to the other side of the equation. And simplify further here. We have P stay the same, K now minus 0.75, and here 0.25. So at the end, what will we have? K to the power of 0.5 with the minus in front, right? And then V times, to the power of 0.25, and W to the power of minus 0.25 equals V to the power 1 on the other side. Alright? We want, what do we want? We want to solve for K. Nah? So first let's cross multiply everything out on the left hand side to the other side. We have K minus 0.5 stay there, but everything else gone. So P to the other side is P minus 1. Now V to the other side becomes minus 0.25 plus 1. So at the end it will be 0.75, right? 75. Alright, very good. Times W, just switch the sign, 0.25. Yeah? And now the next step, we want to get rid of this exponent of K. So 0.5 minus equivalent to minus 1/2, right? And you want to have to the power of 1. So what should you multiply, or what should you raise which power? Minus for sure. That's how we get rid of this minus 2, right? So raise both sides to the power of minus 2. We have k to the power of minus 0.5, raise everything to the power of minus 2, equals p minus 1 v 75.75 w 0.25, right? Everything to the power of minus 2. What will we have? Now on the one side we could already write k start because we get rid of the exponent as a function of p v w equals. Just need to sort out the exponent here. Minus 1 times minus 2 is actually p squared, right? And then v to the power of 0.75 times 2 is 1.5, but with minus, right? Then w minus 0.5, right? And this is the input demand function, but the unconditional one for capital. Next step, we could substitute k start back into what? Into 3. Easy. To solve for L star. So we could write a 3 equivalent to L. Right now we could already write L start as a function of P V W equals V times W minus 1 times K, and K is here. So P square V minus 1.5 W minus 0.5, right? And simplified it a bit further. L start P V W equal, so V to the power of 1, sorry, and then minus 1.5. So V, but let's write P squared in front first, and then times V minus what is left, 0.5, right? And then W minus 1.5. That is the contingent input, sorry, not contingent, but unconditional input demand function for labor. So, very standard approach. After solving for the first order condition of the maximization problem, what can we do? We could plug the solution back into the objective function to arrive in some sort of indirect objective function, right? So what is the objective function of this problem? The profit, right? And we also have seen from the output perspective. And in this case, from the input perspective, it's actually the same. So we plug the unconditional demand function of input K star and L star back into the definition of the profit. So here we have two places where we plug the solution in the first place is the K and L in the production function F. And the second is in the cost part, that is V times K and W times L star. And this is the profit function. Now take a moment to compare the profit functions from the two approaches. What can we see? So you will see that doesn't matter if we plug the supply function for the output perspective case or the input quantity in the input perspective case, they are all the function of prices, that is output prices and input prices, V and W. Now here the same, P, V and W. Consequently, doesn't matter if you take the output perspective or the input perspective to maximize your profit, the profit function obtained from these two approaches should be identical at the end. Keep that in mind. That is important now. So if some days, imagine you become, I don't know, agribusiness consultant, and then a farmer comes to you to ask for your help to maximize his profit or her profit, and then you use output perspective and then you use input perspective, and then the profit function at the end different. The farmer will get in trouble, and I assume you too. Now that's one example of the application. Sometimes you're concerned with why you have to learn all this stuff, boring theories. Now we could also apply the envelope theorem to see how profits respond to changes in output and input prices. Now, do you still remember what envelope theorem is? All right, I write it down first now. So assuming we already solved for the profit function, which is, the function of PVW equals P times F K start P V W L start P V W minus the cost, and the cost is now K start, also the function of prices, input and output, times V plus L start, similar as a function now, times W, right? So that is the indirect objective function or the profit function. Now, so what envelope theorem says is that now at the maximum point, we could fix this K start and L start at their maximum value, right? And treat them as constant. And by that, we could examine the effect of changes in price of the input and the output. So that is the application of envelope theorem. So if we take the derivative of the profit function with respect to P, we will arrive in F, and in this case is equivalent to the supply function. the Q? Does it look familiar to you? It is the supply function that we derived in the output perspective. Now, that's the first thing. And to remind you again why we could do that without caring about P here and P here, because envelope theorem says that at the maximum point, after we solve for the maximization problem already, we could ignore the indirect effect of the parameter, here's the market price P, inside this function, and only focus on its direct effect, standing here P alone. Now, similarly, we could take the derivative of the profit function with respect to V, which is now here, the direct effect only. Now, so then we will arrive again in the minus or the negative of the unconditional input demand function for K, capital, and the same for L with respect to W. And these derivations, these shortcuts are called the Hotterling's lemma. Yeah. Now let's go quickly through the properties of the profit function. We will not prove these properties here because from what I see, you can already understand very clearly and do it very precisely. So I can avoid making the video boring by repeating myself again here. The first property is homogeneity. By construction, if you have done everything correctly to arrive in the profit function up to now, then it should be homogeneous of degree 1 in all prices. That means when you multiply all prices mean both output and input prices. Now, by the same factor t, for example here, t equal 2, that means you doubled all prices. The profit will also be doubled. So, for example, in the times of inflation, when you have the prices of everything in the economy increases by the same percentage, then the profit will also be increased by that percentage. Now, one question may be worth thinking about to yourself is, does that mean you get more profit in terms of real income or not? Yeah, let's think about that. And if you're interested in discussion about that, come back to me. Now, the second property is non-decreasing in output price, which is quite intuitive, right? So imagine now if you keep everything else constant and only the price of the product increases, then your profit should be increasing, right? If not, then probably you were not maximizing your profit at the first place, or you did something wrong with it. That's also one example that I said in the very beginning when we had that introductory week, right? That is one implication of profit maximization models is firms will get more profit when output price increases. Now, next property, non-increasing in input prices. Also quite intuitive, right? So imagine everything stays the same, but one day the input cost for all the ingredients to the pho business example that I said last time, increase. Like veggies, noodles, they get costly. Now, of course, then my profit will decrease. Why? Because I'm selling for the same price what I have to pay more now, right? We could also put it the other way around, like the approach here. So assuming there is a decrease in input price, so your input get cheaper. By not doing anything, your profits already increase. So like you produce the same level and you buy the same input mix, then your profit already increase because now the cost is cheaper for you. However, that is without any adjustment. When you adjust according to the profit maximization, the profit would increase more. Why? This is the technical aspect that we said last time. Remember that we have this graph when we talk about cost. Here's W, right? And here we have a straight line is equal C pseudo. And your cost is actually concave, and below this are tangent, but from below this C pseudo. So that is your C. Why? Because either when the input price increase or decrease, you have the ability to adjust your input mix in order to avoid the increasing cost or to benefit from the decreasing cost of input, right? So that is why from below here and from here is also the actual cost is below the C shadow. Now, and if there's a decrease in input price, you see here, you could benefit from adjusting the input mix. And earlier, we already showed that the profit maximization from input perspective implies cost minimization, right? So this is actually what happens in the background when input prices changes. And that is why profit is now decreasing in input prices. The last property is the convex in output price. So actually, we could apply similar reasoning to this here, but now for output price. So instead, you would also have a graph, but now with pi profit on a vertical axis and output price on the horizontal axis now. And you have a straight line that is pi pseudo, I call it that way. But now for profit is convex. So this is your actual pi. Now, and why? Let's think about the case of price discrimination, and your firm or your business sells products, identical products, but in different locations with different prices. Now, so when the price ratio change in these locations, you could adapt flexibly your allocation of output sold in each location in order to benefit from these price changes. And thanks to that ability or flexibility, your profit will not be this straight line, but it will increase beyond that. Now, you could read more about this in the textbook. Actually, there's a nice application which may be necessary for your assignment this week. So don't overlook that.